Swayam Prabha. Digital India. Educated India.
And the protocol I'm going to describe is a more complicated protocol. I'm going to describe in terms of physical objects like boxes and keys, and they can be translated into a digital protocol with boxes being PRFs or block ciphers with some care taken. But I'm going to not do that. I'll just describe it in terms of boxes and keys. Okay, so first Alice prepares 4 boxes. The boxes, I labeled them by XY, so B00, B01, B10, B11. So 4 boxes. And inside each, so I'll say what is going to be inside each box, but also she'll pick keys and locks. So 4 keys and locks, so they are labeled as, I'm describing the key here, K sub x equal to 0, so there are 2 kinds of keys, x keys and y keys. So x is say the input for Alice, y is the input for Bob, let's say. And corresponding to that, and corresponding to each possible value that this x and y can take, there is a key. So key labeled as x equal to 0, key labeled as x equal to 1, y equal to 0, y equal to 1. And so that's a key and comes with a lock, right? So this key can open that lock. So there's a this kind of lock that you put on. It's a padlock, right? You can put on any box. Okay, so these are the 4 boxes I mentioned. B00, the little thing on top. Here is that label on the box, right? And what's inside the box is a value that I've put in. So I write this value in a sheet of paper, put it inside the box. Okay. So what's the value I'm going to put inside the box? What's the value I'm going to put inside the box? It is R of xy. So B of xy, so say this one, B of 0, 0 will have 0 in it. And all the other boxes have 1 in it because this function is R. And yeah, these were the keys. So so the red is x and blue is y. So and the key has key x equal to 0, x equal to 1, y equal to 0, y equal to 1. So those are the 4 keys. Okay, so this is what I said so far. Alice has picked. Then I also said this. She placed inside the box the bit R of AB. But then she's going to lock this box. And each box she's going to lock using 2 padlocks. Okay? Such that to open the box, you need to open both the locks. Right? So there are 2 locks holding the box shut. And to be able to open, you need to open both the locks. And what are the keys or what are the locks she's going to use to lock BXY equal, say B00, right? She would use Kx equal to 0 and Ky equal to 0. To lock B01, she would use the key x equal to 0 and y equal to 1. Right? So there will be 2 locks, 2 separate locks. Okay, so yeah, that's her locking the box B00 with those 2 keys, with those 2 locks. And I erased the content of the box to say that once it's locked, you can't see what's inside it. Okay, and so all of the boxes are now locked. And then Alice unlabels the boxes and sends them in random order to Bob. So Bob just gets 4 locked boxes with some locks hanging onto them. He doesn't know which lock is labeled 0, which box is labeled 0 and 1 for that matter. And now to compute the function, Alice already has her input x, right? X, it's either 0 or 1. So let's call that input a. Her input variable is called x. The value of that variable is a. So she takes the key corresponding to her input, so key x equal to A, and gives it to Bob, but after removing the label on it, because that looking at it you will know what A is, right, if you keep the label. So you remove the label, and so this is what she is sending. This much is what she is sending to Bob. So the 4 boxes and 1 key corresponding to your input. Now this key is going to open the red lock in some 2 of them and not open the other one. So this Bob can try that, but so far no use, because the lock will open, but he cannot open the box itself because there is another lock on each of these boxes. Okay, so far he has not managed to learn anything from this. But now, now Bob wants one more key. So the whole plan is so that he can open one of these boxes eventually and get the output sitting inside that box. Okay, so what is the key he will need? He will need the key for y equal to b. Okay, so he knows that bit b, and he wants the key corresponding to y equal to b, the blue key for the bit b. Then he can go and open the x equal to a and y equal to b locks on the box bxy. So he'd like to pick it up, but he'd like to pick it up without telling Alice b. And that's exactly what oblivious transfer can do for you, right? So Bob will obliviously pick up one of these 2 keys, one of these 2 blue keys. Which one? The one corresponding to his input. And Alice will have no idea which one he picked up. And Bob will get only one of these keys. He doesn't see the other key. So now he has 2 keys, 4 boxes. There is exactly 1 box that can be completely opened. And so he knows that that's going to be the situation, right? And he can open it, and whatever value in it will be f of xy, r of xy. He knows that, but he has no idea what x was. Well, sometimes he will have, like if his input is 0, then of course the output is x. But if his input is 1, he already knows that whatever box he opens, he will find 1 sitting inside it, and he will have no idea whether x equal to 0 or x equal to 1. Okay? So that's the kind of secrecy we want. He learns nothing beyond the outcome of the function. So is this protocol okay? Seems like rather elaborate for something you could have done directly using OT, right? You could have picked up one of those bits, but we are doing this so that we can do the rest of the protocol.
So the key that Alice sends could be used again for the second lock, and maybe 0, 0 and 1, 1 could be unlocked, right?
No, so what you're asking is Alice send a key which actually opens 2 boxes, right? The locks on 2 boxes, k of say x equal to a. But the other box, you have no idea what is inside the box, because you don't have the y equal to 1 minus b, the other value for y. So say let's take example. So a and b are both say 0. Bob only got the key for y equal to 0. So there is one box which is x equal to 0, y equal to 0. He can open both of them. There's another box x equal to 0, y equal to 1. He can open the x equal to 0 lock, but he cannot open the box. Similarly, there's another one where he can open the y equal to 0 lock, but he cannot open the box because it's x equal to 1. And there's another box where he cannot open either. So this much he already could have predicted what he would see. That's it's 0 knowledge. He knows that there will be these 2 keys. There will be one that will open. There will be one box, both of which will whose locks get opened. There's one in which only the blue key will open, one in which only the red key will open the red lock, and the one where neither would open. That much he already knows. What he is hoping to learn is what's inside that box. So he does learn that. That's some information he didn't have, but that's exactly the information he's supposed to learn, f of x. So he's learning nothing beyond what he's supposed to learn. Okay? Does that make sense? Okay, so yeah, so I think just to answer your questions, in this slide again, why is this secure? from the Alice's point of view, she doesn't see anything. She prepared a bunch of things that she doesn't learn anything about Bob's input B, because the only way Bob's input was used in the protocol from Alice's point of view is here in this OT. And OT doesn't tell you anything about what the choice bit was. So she learns nothing. Bob, what he sees is entirely predictable. Okay, so it's a similar. I didn't give you the security definition for secure two-party computation or multi-party computation. We don't have enough time for that, but it's basically same idea as we had for zero-knowledge proof. It's based on simulation. Your view can be simulated just based on what you're allowed to learn. Okay? In the case of zero-knowledge proof, it was the fact that x is in L. That's something you're allowed to learn. Here it is f of xy for Bob. So his view can be simulated given the final outcome. So there are 4 boxes. There will be 2 keys. Opening the keys have nothing to do with the input values, and one of those keys will open. One of these boxes, will be opened by the 2 keys, and inside that will be f of xy and nothing else. Okay. So the secrecy for OR, the only non-trivial secrecy is when Bob has input 1, the 2 cases, whether x equal to 0 or x equal to 1, appear the same. He opens a box, and inside that will be the value 1. He doesn't know, the other box that when the other box has y key opens, whether it has a 0 or a 1. Sorry, that has a 1 he knows, but the other key that the x opens, corresponding to y equal to 0, he doesn't know whether it has 0 or 1. So that's the security you're getting. All right, so this is okay, but we didn't really gain anything, right? We just made something that we could have done simpler, in a simple way, into a more complicated thing. Let's see how to now use that to solve the bigger problem. And the idea, now this is our bigger circuit. Okay, so forget the unary gates. Unary gates can be pushed to the, say there's a NOT gate, it can be pushed into the binary gate that it's feeding into. So all the gates are going to be binary gates. They don't have to be AND or, they can be AND of x naught and y, for instance, right? Or in this case, if you push this NOT gate all the way here, it will be OR of NOT of the first input and the second input. So it's all binary gates, Boolean functions. And what we are going to do is, for each of these gates, we will do something similar to what we did here. We'll have boxes, keys. Bob will open the box. But in all these things here, when he opens a box, so there will be 4 boxes for each gate. He'll somehow manage to open one of those boxes completely. What he will get will be a key. In the very top one, he will get the value. But in all the others, what he's going to get is a key that can be used in the next box. And to start him off, we'll have him, have the keys for the input wires. Okay, so that's a very high-level idea. Okay, so let's look at one of these gates. So for each wire in the circuit, so wire can be identified as a gate, right? The gate from which the Y comes out. So I'm giving that wire a variable name, so wire W. I'll have 2 keys. For every wire, there will be 2 keys. Okay? Everywhere except the output wire. So in the previous case, there were only 2 wires. When there was only one gate, there was X and Y, the 2 input wires. Now there are many wires in the circuit. For each of them, there will be 2 keys corresponding to W equal to 0 and W equal to 1. Okay, so here are all the keys that are relevant to that gate. And they come in different colors now. And as before, for the input gates, there will be, input wires are also wires of the same kind, so there will also be 2 keys per input wire. I've labeled some of them as red, some of them as blue, saying that the red ones are wires which are owned by Alice. The input comes from Alice's input, and the blue ones are wires owned by Bob. Okay. let's just look at one gate. So for each gate, Alice will prepare these 4 boxes as before, except so what she puts inside the box. So the box labeled as UV, right, kind of corresponds to, so I'm calling UV as the input wires, W as the output wire. So box labeled with UV equal to 0, 0, let's say. So here I'm talking about UV equal to AB. So say box UV equal to 0, 0. Inside that will be a key corresponding to W equal to what? W equal to, say, this Gates function is G, and or and of not, or whatever. So some function G, Boolean function G. So what you put inside, I think that's this capital G here, yeah, right. So what you put inside is a key corresponding to W equals G of AB. So concretely, say there's an OR gate for the B UV equal to 0, 0, you will put K W equal to 0. And for B sub UV equal to 0, 1, you will put K sub W equal to 1. Okay, the key labeled as W equal to 1. So in general, you put, so these 4 boxes, the key sitting inside here corresponds to the key, W equal to the output value. So it's like, every input is now represented by this key, and otherwise we are doing the same thing. So we are keeping the output of the function inside the box. It's just that instead of the actual output bit, we have the key that represents it. Okay, and we'll give, we'll do the same old thing, like unlabel them, which means basically permute the boxes, and send all these boxes, one for each gate. Ship all of these boxes to Bob. And also ship all the keys corresponding to Alice's own input wires, right? 1 key per input wire. So there are 2 keys that she originally picked, right? One of them corresponds to her input, so for each wire, send that. And for Bob, we will do oblivious transfers. Again, 1 per each input wire owned by Bob. He will, so here I wrote B, 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 but they're all different B's, right? He will say, he will feed in whatever bit of input he has on that wire, get back the key corresponding to that wire. And now, what does he have? He has all these boxes for each gate, and he has 1 key per all input wire. For every input wire, he has 1 key. Now, remember the topologically sorted way of this evaluating the circuit. So you can go to one of the gates at the bottom layer. You will have 1 key for the left wire, 1 key for the right wire. You open it, you'll get 1 key for the wire coming out of that gate. So the invariant we are going to maintain is that you will only see 1 key for each wire. Okay, and that invariant is maintained at the beginning, and at every step when you are evaluating one more gate, what you're getting is 1 key for the wire coming out of that gate. Okay? And at the very end, at the top gate, you could actually have the value itself sitting directly. So when you open that gate, you'll get the value. Yeah, so that's what Bob does. Okay? Any questions on the whole protocol? Okay, so it's fairly simple protocol once you see what's going on. So for each wire, there will be these 4 boxes that will need to be shipped for each gate, And so it's not terribly expensive either. It's a fairly realistic protocol. And there are implementations, people have used it for various things. Okay, so that's a gobble circuit protocol. And there are a lot of optimizations. Instead of having 4 boxes here, by the way, the boxes will eventually become some sort of ciphertext. And instead of having 4 ciphertexts, there are protocols which shave it down to 3 ciphertexts, 2 ciphertexts, using some clever things. For special kind of gates, you can do special things. If you're in the random oracle model, you can get some gates for free. So the XOR gate doesn't need any of these boxes if you're in the random oracle model. So there are all sorts of optimizations that have been done. But the basic idea is just this. Okay, I mean they're constant factor optimization. So if you don't mind a factor of say 4, then this is perfectly fine. Just have 4 of these boxes. Okay, so why is this secure? It's a little you have to pay some attention to the argument and convince yourself, but it works. So again, as before, Alice sees nothing. She prepared a bunch of things. She participated in some oblivious transfers as the senders. She learned nothing from that. Now, what we want to argue is that Bob saw a lot of things. He got all these keys. Then he could open various boxes. He got keys out of them. He could open things. But essentially, what he's saying is completely predictable. What I said earlier, right? The invariant that for each wire he'll get 1 key. The key by itself is independent of all data. It's just a random key. And it's only at the top gate when you opens the box that opens for the top gate. Inside that will be the value. So, this whole view that he got can be simulated by preparing boxes which has junk everywhere, or let's say boxes which have arbitrary keys inside everywhere. So each wire needs to have only 1 key really, rather than 2 keys. And but okay, I should say the content of the boxes need to be only 1 key, but they're locked using 2 keys. You could just simulate it using kind of keys all through, except the very top box you need to put a value, and that will be f of xy. Right? So you basically do the computation with an arbitrary, you could imagine running the protocol with an arbitrary x for Alice's input. Okay? And so you prepare all the boxes exactly like Alice would have done with an arbitrary input, except for the top box. Just make sure that inside that, say in every box you put the value which is output value. And that will be a good simulation. How much time do I have? So this is my last slide about MPC, and I want to kind of take a little detour and say something else. Okay, but any questions before I do that? All right, so the last kind of little musing, this part is about kind of philosophical or kind of policy questions of cryptography and how it should be governed. Okay, and there's of course not, unlike the rest of the lectures we had, there's not scientific. It's more about kind of a perspective, my personal perspective. But it's good to keep this kind of a big picture of where cryptography fits into society. And historically, cryptography was considered something related to military and intelligence and espionage, and that's the background from which cryptography was developed through world wars and by the governments. And even actually go way back to the time of Caesar, we know about Caesar cipher, and that was also in the context of sending secret messages to the military in the field. In the Second World War, there is this famous center that was run by British government called the Bletchley Park, and that's where people like Turing actually worked on breaking ciphers. They collaborated with other people in Poland and so forth, but they had a lot of success in building big computers and breaking ciphers that were used by the Axis forces. And because of all this kind of focus on using cryptography for military purposes, until a few decades back, until the 90s, in the US, for instance, encryption or block ciphers were classified as auxiliary military equipment. Right? It was considered military equipment, and that came with export restrictions. So if you built some software in the US which used a strong encryption algorithm, You're not allowed to put it up on the internet or sell it to some people outside the US. That was a law till the 90s. Okay, and of course that didn't look very meaningful, because something like RSA, which was considered one of these things falling under the export restriction, is just some mathematical function which is published and everybody knows about it. What does it mean to say if your software has this thing, don't show it to people outside the US? So this is a funny T-shirt. Says this shirt is classified as a munition and may not be exported from the United States or shown to a foreign nation. And this RSA encryption algorithm written in Perl. So this is considered a weapon, or at least an auxiliary military equipment. Of course, laws were relaxed later. Didn't make sense, and it was a matter of time before they were changed. So that's kind of the historical perspective coming from the military side of things. Another perspective is from the law enforcement side. So people like, in the US, FBI, or in India you probably have CBI or something, right? For law enforcement, from the perspective of law enforcement, there's a nuisance in many ways. Cryptography is a nuisance in many ways. And one is that there is, some of it is also a nuisance for, that hits common people. And one example is ransomware. So this is what happened in Ames, a few days back, right? Your data gets encrypted, and the malware asks you for, money, cryptocurrencies, so that they will give you the decryption key, and you don't know if they will actually give you the decryption key or not. And this worked only because there is encryption, and the encryption is strong, right? There is no way you could decrypt it. There's no hope to decrypt it unless you got the key. Okay, so that's ransomware. Of course, many ransomware attacks got thwarted because of bugs in the malware, like the encryption scheme used as buggy or whatever. So sometimes you get lucky and the ransomware doesn't work, but sometimes it works. Extortionware, a kind of similar idea. They will take your photos, or they'll say, oh, we've found all the websites you went to or that you paid money for this thing. We have records of that. We're going to post it on Facebook unless you pay us. Okay, and it could be true, it could be false. More often false than true, because it's much easier to say that you have somebody's private information than actually try and get the private information, right? So you just get some mail saying, oh, we saw that you did this bad thing and we are going to tell everyone unless you pay us money. That's extortionware. That's not so much of cryptography there, but it's a malware. The dark net is, all these websites which are not accessible in the normal way, but you have to kind of go through anonymous networks, use special browsers, special software to access them, and you connect to servers that you don't know where they are in the world, and the servers wouldn't know who is connecting to them either often, and that's the darknet. And in the darknet, a lot of things might be legitimate, but also there are a lot of things that are illegitimate or illegal in many countries, right? You can sell and buy things which are illegal on the darknet. So, and the darknet is also enabled because of a lot of cryptographic tools. And cryptography provides these very robust ways for people to communicate with each other, but that also means those people could be, considered, all those communications could be considered illegitimate by the governments or by other people. Or one government might consider what's happening in another country as illegal activities for them, right? So, so everybody, once you have secure communication, everybody can use that, and including rebels or terrorists or enemy countries and so forth. Okay, so this creates a lot of headache for law enforcement, and as I was saying, it's all enabled by these very strong cryptographic tools that we have. Encryption, cryptocurrencies, anonymous networks, and they can be frustratingly effective when properly implemented. So what do governments do, or what have they done? So in the 70s, for instance, public key encryption I mentioned was invented in GCHQ by people like Cox and Williamson, and it was not published. Okay, it was such a powerful, useful, enabling tool for us now, but at that time it was not published because it seemed like a dangerous thing. In 75, when these block ciphers were getting standardized, NSA restricted the size of DES, the digital encryption standard, the key size of DES, so that it would be breakable by some, a lot of computational power, with some lot of computational power, but still, they didn't want it to be too strong. On the other hand, so that's NSA, with its tentacles. But to their credit, it also, should be mentioned that there were some flaws in DES that NSA knew about, and they got it fixed before it was standardized. So NSA had some attacks that worked against the initial proposal for DES. So they didn't tell anyone that's the case at that time, but it was fixed before it was standardized. Another thing I already mentioned, again in the US mainly, was that strong cryptographic components were regulated. They didn't want people, in particular people outside their country, to use strong cryptography. Another very kind of famous thing that happened in the 90s, this was called the crypto wars, was that the government wanted to eavesdrop on everyone. Okay, so this is the time when internet is coming up and people are using encryption, email encryption and so forth. And the government was worried, government as in mainly, agencies like FBI who are used to, tapping phones and listening to people. They got worried that now people are using encryption and we won't be able to do surveillance. So they suggested that all the computers, that all the processors that Intel or whoever will make will come with a chip called the Clipper chip, and encryption should be done using that. And there's a master key that the government will have that will enable them to decrypt things that are encrypted using this Clipper chip. Okay. So this is called escrow, key escrow. The government has a master secret key. It's for safekeeping, but if necessary, they can take that key and open anybody's communication. That was a rather, like there was a lot of heated pushback from the academic community, from the business community, and so forth, and the plan was dropped, thankfully. That doesn't mean that the government stopped worrying about breaking encryption, and the Snowden revelations that we referred to yesterday showed how, so this was specific to the, the Five Eyes. So these are English-speaking countries which are together, they have an alliance. So US, UK, Canada, Australia, New Zealand, doing surveillance globally. Okay? And as part of that, they had these programs like called Bull Run, Edge Hill, Bull Run in the US, Edge Hill in the UK. And the idea was to discover vulnerabilities, software bugs, whatever, right? And instead of getting them fixed, use them, exploit them. Okay? So the government, these programs, they were sitting on collections of vulnerabilities only, that they discovered and didn't tell anyone about. At least one instance of one of those vulnerabilities leaking, it's believed that at least one of those things, malware called WannaCry, was actually based on one of these things that was discovered by the government agencies and not disclosed. And eventually it was rediscovered and, or rather maybe leaked. and then was exploited in the wild. So if they had got it fixed, that wouldn't have happened. Another thing that the governments have been caught doing or suspected to be doing is backdooring standards. As I mentioned, there was some standard, some elliptic curve based pseudo-random generator, and it was a weak curve. So the group, the discrete log problem was not hard enough, for instance. The last instance I have on the slide is this tension that came up between FBI and Apple. So iPhones were confiscated from criminals, and FBI wanted to open them, to unlock them, their encrypted storage. They want to read it, and asked Apple to do it for them. And Apple didn't, didn't help. But eventually, that particular instance, they managed to break it because of some other vulnerability in iPhone, and they got it done without Apple's cooperation. But the point was the government and the software companies were in opposing ends. The software companies want to provide, or at least they want to look like they're providing security to their users. The governments want a way around it. So what should we do? Like there's this, kind of fairly legitimate concern about law enforcement, all these bad things happening using cryptography, and the government reaction to that to kind of clamp down on how well you can use cryptography. What is the right thing to do? Okay, maybe it's a philosophical question, there's no straight answer, but here's the thing. Okay, so cryptography is used for illegal activities, but it's also fundamental protection that all of us rely on a lot. Okay, so just to give an analogy, I'm not sure how convincing it is, but think of something like masks. Okay, they are important for the public. We had it used in the pandemic a lot, but it also helps criminals. So if you outlaw masks, if you say nobody should wear a mask, well, it comes at a cost, right? Maybe it's not so in the balance of things. Maybe a few criminals wearing masks and robbing a bank, say it's not as problematic as everybody falling sick and a lot of people dying. So you need to kind of see how important this notion of proportionality. If you do some regulation, is it proportional to the or the motivation for that regulation, is it proportional to the impact it's going to create on other people? Okay. And the bottom line is that even if the governments put in a lot of regulation, the criminals or the terrorists or whoever are not going to be deterred by that. Just like that T-shirt was there, anyone with enough some amount of know-how can employ strong cryptography. They can get around it, or rather get around the regulations. Right? They can do it in a way, even if it's illegal, it may not be detected, then they can do it without any consequence. On the other hand, law-abiding citizens and institutions will be forced to not use strong cryptography. So the general population will not be able to use this cryptography if you have this regulation saying you shouldn't use strong cryptography. Cryptography is what we have come to rely on for a lot of things. Commerce, journalism, democracy, safety at various levels, national security, right? So even if you're worried about the foreign states launching an attack on you, if your citizens are not using good cryptography, they can attack your citizens. So regulating cryptography in some sense gives us worst of both worlds. People who you're worried about having all this dark net and doing illegal activities there, ransomware, they will still do it. And of course it's illegal, maybe illegal, but who cares? And ransomware to begin with could be illegal. That doesn't stop them from doing it. On the other hand, it will prevent legitimate use of strong cryptography. So it's kind of pointless to try and regulate cryptography. What governments should do probably is to help everyone use cryptography, the best cryptography available in the best possible way, right, correctly. And eliminate the chance of bugs. So currently, governments or law enforcement are looking forward to there being some bug in some encryption algorithm or some standard software so that they can exploit it. That's just backwards. What they should do is help everyone get their software running correctly and help the whole kind of general population be secure, and not worry so much about a few criminals who may may anyway manage to do it securely, because at least the ones who are sophisticated enough there would anyway be able to do it well. They'll be backed by state actors, right? So even if it's illegal, there will be like high quality software that can be built outside of your country and they could be used. So you'd want to have everyone use high quality software. Another thing is data privacy legislation. India has something in the works. There are a lot of concerns and issues there, but so yeah, that's something that's needed, a proper something that will force not just companies to kind of respect privacy of the consumers, but also governments to respect privacy of the citizens. Okay, and that's one big gaping hole in the data privacy legislation. They always exclude the government from any responsibility of privacy. And as I was saying, the governments try to weaponize vulnerabilities by keeping them secret. That would backfire. Or they might backfire either because they could leak or they could be rediscovered. And if everyone is using these softwares with vulnerabilities, then it's a big problem for everyone. Okay, so the last little bit here is saying, it's not just about security. There's also a lot of things about trust that's beyond cryptographic security, right? Things like phishing attacks or fake news. Get all these WhatsApp forwards, which are there's a social element to it, and somehow we need to help protect people against that, but not by resorting to censorship. You could say, oh, there is a lot of fake news, so I'll have a law saying anybody publishing fake news will be put in incarcerated for like 10 years or whatever. That kind of censorship is also not good, right? That'll actually give a way to propagate fake news while suppressing the real news. So there's a tension though between anonymity and accountability, between kind of privacy and integrity. And how can we fix that? Maybe some of these cryptographic tools like secure multi-party computation would be the answer. At least they can give new options, like our example of the no-fly list, right? You can get both, kind of security for both sides. You can get your accountability, namely people who are not allowed to fly cannot fly, and also anonymity, that if you are not supposed to be in that list, the government cannot do surveillance on you. So there are potential cryptographic solutions that can change the options, and of course, there's a lot of need for people being educated to stay away from scams and fake news, or installing or updating their software and so forth. So yeah, all of that is all I want to say. So there's a whole lot of cryptographic tools out there, underexploited, and there is a lot of potential to use them towards a kind of more empowered future. Okay. All right, having gone way over time, so I'll stop now. I'll be around once in a while. You can ask questions through Mookle or others who will be here. Okay. All right, so I'll just stop with that.